Hello, I'm Mr. Muskaluk, your AP Chemistry teacher at ChemAdvantage.
We've got here a pretty complete problem for stoichiometry. It involves limiting reactants and is pretty complicated. And if you understand how to do this type of limiting reactant problem, you can probably master almost any of them. So this is worth your time and, of course, your understanding. The reaction is one where we've got coefficients that are not all one. We've got two ammonias reacting with a carbon dioxide. And if you've got liquid ammonia and frozen CO2, it's possible to make this compound that I've got highlighted here, urea. It's got two amides attached to a CO. Very important compound. And also we get some water. Let's just take a quick detour to find out a little bit about urea. It's got an interesting history and tons of applications. Here's the compound. When you produce it, it's a white solid. And as I said, here's our carbonyl group, our carbon with a double bond oxygen. It's got two amides attached to it. It should be called carbonyl diamide, but nobody calls it that because this was discovered a long time ago, back in the 1720s. And it was isolated from urea. So it's kept its name. And there are hundreds of millions of tons of this produced each year. But let's quickly look at just some of the things that they have. Agricultural, 90% is used as a fertilizer, very high nitrogen containing fertilizer. Resins, explosives, in automobiles to decrease pollution. Laboratories, it denatures proteins. And they have got a whole host of uses in terms of medicine. It's got a lot of biological activity. And then the miscellaneous here is dish soap, dyeing, and protein and ocean nourish. I mean, even in pretzels. But actually, in terms of physiology, the important thing is that you produce your own urea. When you digest proteins, you make a significant amount of this stuff. And the Dutch scientist, Herman Boerhaave, ended up isolating. He took a bunch of urine, boiled it, filtered it, removed a top liquid, dissolved the solid, and recrystallized to make this urea. It was considered to be a biological organism. And it used to be thought that biological molecules, in terms of vitalism, is that only living organisms can make compounds like this. And urea is a relatively complicated one. But another chemist, here we had 1727 when it was first isolated. And then about 100 years later, Friedrich Wöhler, who's very famous for this, he took some silver cyanate, this is a mineral that you can get, and ammonium chloride, another mineral, and he made urea. And this was pretty important because it showed that you could make biological molecules. You could make things that organisms make without having to have the organism. And here's his quote: "I must tell you that I can make urea without the use of kidneys, either man or dog." And he did. He found this compound, made this compound, and it's synthesized now, like I say, by hundreds of millions of tons each year. But I think it's time to go. Oh, wait a sec. Let's just quickly go here. We've got the American Chem Society site, and they have a number of interesting articles on urea and its uses. So take a little diversion and see what this is about. I mean, you're making urea right now, and here's its chemical nature, and we're going to do a problem using it. So let me pull the problem up. In the problem, we've got the reaction, carbon dioxide and ammonia, and here's our urea. In one reaction, we're mixing 297 grams of ammonia, quite a bit of it, and this is like a pound of carbon dioxide. And we're mixing this ammonia and carbon dioxide to make these products. Here's the reaction. You're given both reactants are given. And when you've got the reactants given, you have to worry, do I have the right amount of things? Because a chemist should know. I mean, we can figure these grams and weigh them, but what do we get, and do we have anything left over? Limiting reactant problem. And the only way you can approach these is to forget about the grams. I mean, grams is just, we measure it by how much this mass is attracted to the earth. It really doesn't tell us how many molecules, how many ammonias we have. It just tells, okay, it's got this much mass. So we have to change the mass into the chemist's mole, which is the number of molecules. By now, I hope that you can find the molar mass of ammonia and convert grams into moles. Divide by molar mass. 14 for nitrogen, 1 for each of these hydrogens adds up to about 17. I did it to 4 significant digits, and I have 17 moles of ammonia. By the way, ammonia, the name, should be nitrogen triiodide, but this was found in ancient Egypt, and the Amun-Ra name ammonia has stuck. Here we've got 594 grams of carbon dioxide, but now we divide by carbon dioxide's molar mass. This one you should remember, 44.01. It's used a lot. Sometimes you don't need this one. 44 would have been enough, but again, 4 sig digs, and I had to do things correctly here. Yeah, I'm a chem teacher. And it's interesting. Here you've got about a pound of carbon dioxide and about a half a pound of ammonia. You think you've got more carbon dioxide than you have ammonia, but when you actually look at the molecules, you've got less carbon dioxide. You're sort of short on carbon dioxide because these molecules weigh more. So since they weigh more, this mass is going to contain fewer actual molecules. So it sort of reverses things around. That's why this is a sneaky problem. You say, wait a second, limiting reactant, probably the ammonia. Nah, sorry, not right now, not based on grams. Let's look at the moles. Now, next step, once we got the moles, look at the reaction. The reaction says you need 2 ammonias to 1 CO2, and this isn't grams, this is moles. So you're going to need twice as much ammonia as you have carbon dioxide. Now looking here, you can see you don't have twice as much ammonia. Here you've got 13, twice as much of that, it'd be 26. So we're going to be shy of ammonia. We're going to have to get more of this ammonia. Now, this one's pretty obvious, and you should have used your reasoning powers to say, ammonia, I'm short of. It is my limiting reactant. I should have had more of it. But if this had been a little bit more difficult, if this had been a 5 and a 7 or a 13 and 9, it would have been tougher to figure out. So this technique, which is a fast one, will always let you find the limiting reactant. Limiting reactant, you only look at the reactants. Forget the products. You take the mole amounts. We don't use grams. Don't use grams, please. You'll embarrass your chemistry teacher. You take the moles and divide by the coefficient. Take the moles and divide by the coefficient, and here we go. We got 17.86 produces 8.730 moles. I put this 0 here to show significant figures. And that is my reduced amount. Well, this is going to be an easy division, but again, I had to show it, and it's 13.51. So divide by the coefficients. The smaller amount will be the limiting reactant and will be the thing that you're going to focus on. This is the ammonia, the limiting reactant, which we'd figured out anyway. But this is a fast way of doing it, and it's sufficient if you show it on an FRQ. If these reduced amounts were identical, then we know we would have stoichiometric amounts that we wouldn't have to worry much. We'll know that they'd be completely used. But in this case, we know we're going to have some leftover carbon dioxide because we have more than we need. So answering the question, which substance is the limiting reactant? And we'll just write that out. Now that's what you'd want to write on an FRQ, what the limiting reactant is. 17.46 moles of ammonia is our limiting reactant. Now, you've done this reduction, but you only use this to find the limiting reactant. The important thing is say our limiting reactant is ammonia, and when we do our calculations for the stoichiometry here, we're going to use the original amounts. Forget these amounts. When you do your ice chart, initial, change, end, later on this will be equilibrium when we get more complicated. You use the amounts before you divide it by the coefficient. So let's put those amounts in. We had the original amount, 17.46 moles of ammonia, and we have 13.51 moles of CO2. Put those in the initial row. Again, don't use these. Use the original reactant amounts. Now, the limiting reactant, this 17.46, is going to be completely used up. So in our change, this 17.46 is the amount that without doubt is going to be used, and we'll have none of it left. Once you have a change amount, once in an ice chart you've got the change, you can find all of the other amounts. The change amounts are governed by the limiting reactant, and they'll follow the same coefficient ratios. And I see we have 2 here and a 1 here, so we'll have half as much carbon dioxide. Half of 17.46 is 8.730. That's how many moles of carbon dioxide will be used. That makes sense. 2 to 1. You only use half as much carbon dioxide. We had 13.51. This is the one that's in excess. So we're going to have left over, you can do the subtraction, carbon dioxide. Now the amounts that are produced, these are going to be added. Our change row is still governed by the limiting reactant. So I'll have, because there's a 1 there, 8.73 CO2. That's based on my 17.46, 2 to 1. And of course, we have a 1 here and a 1 here. These will be the same values. The change amounts will be identical in terms of proportions as the coefficients. Well, that makes the water easy to figure out. That's going to be 8.730. This change row is just amazing if you get one of them right. In this case, the limiting reactant. All the rest can be found using the coefficients. Now, with the two amounts, the initial and the change, you can find the end amount. So that first subtraction is going to be one that you'd expect, 0. No ammonia left. It's the limiting reactant. But we're going to have leftover carbon dioxide. There it is. Do this subtraction, and you're going to have 4.78 moles of CO2. We'll change that to grams later. And we'll know exactly how much of this urea is going to be produced. So our N moles, we didn't start with any, so we get 8.73. That's an easy addition. And also, we're going to get the same thing for our water. Now, changing to our grams, well, that's where we multiply by our molar masses. And we're going to get, of course, 0 grams of ammonia, if this reaction had gone to completion, but it really doesn't. Now, here, the CO2, remember we multiply by 44, and that will give us our grams left over. 210 grams. Now, we started with 597 grams, and we've got 210 left over. We didn't have to put that much CO2 in. We could have just put in the original amount, this 8.73 moles of CO2, and that would have been sufficient. But we put in 13.51, so we got some leftovers, some extra CO2 that you're going to have to get rid of. Now, here we've got our urea, and let me pull up my calculator because we didn't have the molar mass of urea, and it's a little tricky. I hope that you could do it, but let's just double check. We've got nitrogen, which is 14.01. Now, you might think there's only one of them, but parentheses. This is the amide group, so we've got our parentheses too. So we actually have 2 of them. So be careful. As soon as there's parentheses, you're going to have to do some multiplication. So that's my nitrogen. And then, of course, I've got my hydrogen, which I hope by now you know the molar mass of. And let's see, we have 2 times 2, so that's going to be 4. And we'll have our molar mass of urea, except I forgot about the carbon, plus the 12.01. And I could have just used 12. And, of course, our oxygen for that total mass. And there we have our molar mass of urea, 60.06 grams. And we'd multiply that times our 8.73 moles. Grams, moles times molar mass will give us the actual weight of urea we produced. 524 grams of this urea is what's produced. 524 grams. I've given it to 3 significant figures because I see the CO2 has got 3, and I'm left with that. And of course, you're going to have your water here, and I'll pull my calculator out again. And I'll take my 8.73 again, 8.73 times, remember the molar mass of water, you're going to use it. Without doubt, that'll be enough, 18.01. And we get our 157 grams of water that is produced. So let's put that down. And this is at the end. At the end, we're going to have 210 grams of CO2 leftovers, 524 grams of urea, and 157 grams of water, and no ammonia is going to be left. So the mass of the ammonia, 0. Carbon dioxide, 210. The leftovers. The urea, 524, and the H2O will be what we have at the end. Calculator. So I'll take my water and add to that the 524 and add to that the 210 CO2 that's left over that wasn't used. In a limiting reactant problem, you've got to remember that there's going to be some stuff left behind that is going to be at the end, your final mass. And we've got 891 grams left when we have this reaction completed. And let's write that down. 892 grams. Now, there's conservation of mass. If you really want to check to see if you did this right, find out what you started with. Now, we have the moles here, but remember they gave us the original 2 amounts. And I'll take those on my calculator, and I'll take that 594.6, the CO2 that I started with, and the 297.3. Let's see if I did this right. If I get 192 grams, I know things worked out. Oh, let's keep our fingers crossed. Enter. There we go. We have 891, and we've got our rounding errors here. That's close enough. This is perfect. This works. You've confirmed everything. The problem is solved. You've not only made urea, but you've solved it while you did this problem. All right, last question. Which reactant was in excess? Well, we know the CO2 was in excess. We've dealt with that quite often. And we figured out the grams that were left over. If this been an FRQ, and it very easily could have been one, this would have solved everything. These ice charts are beautiful. You can take a problem like this, and as a chemist, you can say, hey, you mix this stuff together, this is what you're going to get. I can tell you what you start off with, and in the end, I can tell you what you got. Hey, that's the job of a chemist, and it's also something that's worth knowing. So, solve this problem.